Questions and problems for chapter 23, except for the last section or two which deal with capacitors in series and parallel, and we'll be dealing with that soon. At any rate, what we've got here are three resistors. They're in series with each other, and you have a graph that looks like this. And the question was which of the has the most current going through it, and which is the greatest resistance to lowest resistance. Well, the current has to be the same at all points because this is a series component. The current coming in over here has to go through R1, R2, R3, and then out. So it's the same everywhere, as is true in any series circuit. For part B, if I look at this, the change in voltage has got to be larger across the resistor with greater resistance. So we know through Ohm's law that V equals I times R. If the current's the same through all these, then this, which is the steepest, would have the greatest resistance. This, which is the next steepest, would have the next greatest resistance, and this would have the least resistance. So R3 is greater than R1, is greater than R2. For question 9, it's asking you to figure out how the potential difference from A to B compares from the potential difference from C to D. And it told you that these were the same batteries, and each resistor was identical. So there's 3 resistors in this circuit, 1 resistor in this circuit. So the potential difference across AB and CD has got to be the same, since those regions encompass all the places with voltage drops or resistance. So although all that voltage will be used across this one resistor, and that voltage will be lost across 3 of these resistors, the particulars of that are that all this voltage drop is between C and D, and all this is between A and B. And that would equal the potential difference across the battery. So when I look at this, it's asking to rank the currents. So since there's one resistor here and the same voltage across this battery as this battery, we would have I is equal to delta V divided by R. This has lower total resistance, so this has greater current. I2 and I3 have got to be the same because this is a series circuit. So current everywhere in a series circuit is the same, although current in different series circuits with different batteries and different resistances could differ. But in this plate circuit, there's only one path, so these two have got to be the same current. For problem, oh, that's my finger. That's weird. Problem 9, we've got 6 volts, 2 ohms, 1 ohm. It says, it gave you this graph, and it asks you to actually show what the circuit looked like. So if it's 6 volts and 2 amps, that means the total resistance is 3 ohms. And I know that I'm going from 0 to 6 volts at some point, so the battery would be 6 volts. So if I start here, I would drop these 2 volts. Well, if I have 6 volts and 2 amps, again with 3 ohms, that means this would be the 1 ohm resistor be the one I would encounter first. I'm only dropping 2 of the 6 volts here. At 0 volts, then I cross this, where I'm going up all 6 volts. The wire is where the voltage is flat, and then I lose 4 volts here. 2 amps times 2 ohms means I have a potential difference of 4 volts, and I go from positive 6 to positive 2. And that's where I end up, which is the same location where I started. For P21, it was asking you how many different arrangements you could have with 3 1000 ohms or 1 kilo ohm resistors, and what those resistances would be. The ones I could think of were 3 in series, which is pretty straightforward, so that's 3000 ohms, 3 in parallel, which is a total resistance of 333 ohms, 2 in parallel, and 1 in series. So those would be equivalent of 500 ohms plus 1000 is 1500 ohms. And this was the toughest one for me, 2 in series with each other, but they're in a parallel branch with the other one, which is 1000 ohms. So I would add those 2 up, and that branch has 2000 ohms, this branch has 1000 ohms, 1 over 1000 plus 1 over 2000 equals 1 over R. The equivalent resistance of this is 667 ohms. So the last one was tricky for me. This one was not. These two are pretty easy. So going to problem 22, for Kirchhoff's loop rule, all the voltage provided by both batteries, so 3 volts plus 4.5 volts, which is 7.5 volts, has got to be used up across all three resistors. So we're shown that we've got 3.5 volts and 2 volts across here. That means we've got 2 volts left across this. So if I have 2 volts across 150 ohms, that tells me the current through this must be 0.0133 amps. If you have batteries facing the same orientation, like these are, you add up the voltages. If they're an opposite orientation, you would subtract the voltages. So P30, I think, is asking for the total current through the battery. So what I ended up having to do for this is I drew a lot of different diagrams to get that equivalent resistance. So I hope you take the time to look through there, because it's kind of complicated, but once you get the stepwise process, it's not too bad. So this was the original circuit with all those resistances labeled. In this very outermost branch, the 10 and the 2 are in series with each other, so I can add those up and get 12 ohms. That 12 ohm equivalent resistance, which I've circled in green, is in parallel with this 6 ohm equivalent resistance, which I've got in purple. So overall, this whole outer amount in red is going to be a 4 ohm resistor. You might say, well, why didn't I take these two into account? Well, the problem is how do I do that? Is this in series with this? Is it in series with this? Until I redraw it, it's hard for me to see. So when I redraw all this outer stuff as a 4 ohm resistor here, now I can see that this 8 ohms is in series with all of that. So the 4 plus that 8 give me 12 ohms again. It's in parallel with the 6 ohm again, so once again I get 4 ohms. Now for this outer whole purple region. So now all this is replaced by an equivalent 4 ohm resistor. It's in series with another 4 ohm resistor, that's 8 ohms, and that 8 ohms is in parallel with this 8 ohms. So 1/8 plus 1/8 is 1/4. So all this in red now is 4 ohms. So I redraw again. 4 ohms and 6 ohms is 10 ohms. They're in series with each other. That 10 ohms is in parallel with this 8 ohm. So I get my equivalent resistance of 4.44 ohms. 6 volts divided by 4.44 ohms is 1.35 amps. So if you notice, I'm not trying to skip steps. I'm trying to handle things quite methodically. And it took a while, and it took me several different diagrams, but I'm pretty confident in that answer. For problem 33, this is asking for the current through and the voltage across each resistor. So in this case, it's a 12 volt power source. We've got 3 ohms here, and then we've got these 3 branches, and these are actually in parallel. So I could redraw this like this to make my life a little easier in terms of understanding things. And just like how the diagrams can make it easier or more complicated to figure out, the diagrams don't really look like the wires you see on your table in lab either. So these 3, a quarter plus a 48th plus 1/16, end up being an equivalent of a 3 ohm resistor. So I can say that all that's a 3 ohm resistor, this is a 3 ohm resistor, 3 plus this equivalent 3 would be 6 ohms total resistance, so the total current is 2 amps. So there must be 2 amps through this 3 ohm resistor right here, and 2 times 3 ohms is 6 volts. So I did these 2 things first. I solved for these first, because the current was actually the total current, and V would be just I times R. Now remember, for Kirchhoff's loop rule, in each path, the total voltage drop must equal 12 volts. So if I have a voltage across this 3 ohm resistor of 6 volts, which I figured out, now if any particular charge goes this way, or that way, or that way, there's only one resistor in each path, and so we've got to lose the other 6 volts across each of these. Doesn't matter which path the charge would take. So I did this next, and I figured that out, that this was 6 volts, 6 volts, and 6 volts. Now it won't always be everything is exactly 6. It happens to be because this resistance is 3 ohms, and all 3 of these equivalent are also 3 ohms. So now I'm going to do last, figure out the current through each branch. I've got 6 volts across this 4 ohm resistor from here to here. 6 divided by 4 is 1.5 amps. 6 volts across this divided by 48 is 1/8 of an amp, 0.125. 6 divided by 16 is 3/8 of an amp, 0.375. And that's how those round. 62 I like a lot. It is sneaky, sneaky, sneaky. So at point 2, it's basically asking for the potential points 1, 2, 3, and 4. So at point 2, the potential is 0 volts. Why is that? I've got 0 volts over here, and I can touch point 4 and point 2 without crossing any resistors. So this is basically an ideal conductor. So all 3 of those places, here, here, and here, must be 0 volts. Point 1 is obviously at 10 volts, and point 3 is also at 10 volts. Again, I can get to point 3 without passing through any resistors. So if I look at this, there's actually an interesting combination of paths available. If I look at this, this is one path. It only goes through one 10 ohm resistor. This is a second path, also only goes through one 10 ohm resistor. This is a third path, also only goes through one 10 ohm resistor. So believe it or not, this is basically a circuit like this, not with this thing up here, but it's got 3 10 ohm resistors in parallel. It's just drawn very differently than we would normally expect. So I would end up having 10 volts potential difference divided by 10 ohms in each path. That's 1 amp through each resistor. So in this case, the current goes to the right through this 10 ohm resistor, and then down through point 2 and to the end. Because if it's got a choice of going through no resistance or some resistance, it's going to go through no resistance. Here, the current goes up through the top, down to point 3, and then it goes to the left through the 10 ohm resistor, and then again through the path of no resistance. And then here, the current can come up through the top and then go through that 10 ohm resistor. So in each of those 3 paths, there's a single resistor, and it's 10 ohms. Since I've got 3 10 ohm resistors in parallel, the total resistance of the circuit is 3.33 ohms. Problem 72 is asking for the current through and voltage across each resistor. Notice I'm being careful with how I word that. So the first thing I'm going to do is find the total resistance. I'm going to call this 24 ohms with an asterisk, this 24 ohms with a dot, just to keep them different from each other and so I know which one I'm thinking about. So the first thing I'm going to do is simplify the resistance. 8 and 24, using the rules of parallel resistance, give me 6 ohms. This 6 is in series with this 6, so 6 plus 6 in series is 12 ohms. So this simplified diagram has this middle branch now as a 12 ohm branch. The outer branch is a 24 ohm branch. Well, that can give me an 8 ohm total equivalent resistance using the rules for parallel circuits. All that is in series with 4 ohms, so I have 4 plus 8, that's 12 total ohms of resistance. So the total current is 2 amps, 24 volts divided by 12 ohms. So now I've put all this stuff together to get a single equivalent resistor and a single total current. And I'm going to go back and break it down. So in this case, the current, 2 amps, is going to be all going through the 4 ohm resistor, so that's what I would solve first. V equals I times R, 2 amps times 4 ohms. It's me 8 volts across the 4 ohm resistor. Next, I'm going to probably attack this 24 ohm resistor, because if you look after the 4 ohm, that's the only thing in that outer path. So if I know I use 8 volts across this, and I have 24 volts total, I would have 16 volts left to use across this. So I said 24 total minus 8, 16 volts. Why? Because in any complete path, you've got to use up all the voltage provided by the battery. That's 24 volts. We used 8 volts here. There's 16 volts left. Next, to find the current through this, I'll do 16 volts, which is the voltage across that specific resistor, divided by 24 ohms, which is the resistance of that specific resistor, and I get 0.67 or 2/3 of an amp. From there, if I know that I have 2 amps total going through this and 2/3 of an amp going through this, I should be able to figure out using the junction rule how much current's going through this. That would be 1 1/3 amps, and that's the next thing I did. It's marked 5th. If I know I've got 1.33 amps through here, 1.33 times 6 gives me the amount of resistance, or pardon me, the voltage. That's 8 volts. So now I've solved everything about except for these two. So there's a couple ways we could do this. And this is the 8 ohm and the 24 ohms. And these are things that I'm doing last. So if I know I've got 24 volts and I used 8 volts across this, and I used 8 volts across this, I've got 8 volts left, whether I take this path or this path. There's the other ways to think about that, but I think that would be the easiest way. So I can solve for this as an 8 volt, and this is an 8 volt potential difference as well. Now to get the current, 8 volts divided by 8 ohms means I've got 1 amp in that branch. 8 volts divided by 24 ohms means I've got 0.33 amps in that branch. If I want to do a mental double check, these two, the currents through these two resistors should equal the current through this, and they do. 0.33 plus 1 is 1.33. 1.33 amps through here plus 0.67 amps through here equals 2 amps, and that is my total current. And I think that's it. So hopefully you listen to this and you go through them and take a look at what you have questions about.